Alright, YouTube, we're back. Let's do 108. See this 108? Yes, it is. Second order differential equations applied to Hooke's law without friction. And 109 we'll throw in the friction constant like we did before. Alright, so the force equation for a spring governed by Hooke's law is F equals ma is directly proportional to y, and it's a resistive force, a negative constant proportionality, negative k. So a is y double prime, so my double prime is negative ky, so y double prime is negative ky over my. And let's take a special easy case where the constant negative k over m is negative 1. Based on your work from packet 107, differential equations of this form, y double prime equals negative y such that k equals m, can have the general solution y equals sine or y equals cosine, depending on initial conditions. So let's show that the linear combination y equals a certain number of cosines plus a certain number of sines of these two general solutions is also a solution, it's a more general solution. And then find the constants a and b given some initial conditions. Let's say y of 0 is 5, so you've stretched out the spring 5 units. Y prime of 0 is 0. Y of 0 is 5 inches, so you stretch it out 5 inches, and y prime of 0 is 0 inches per second, so it's a moment right before you let go, the spring is not in motion, then you let go, right? Okay, let's try that. So 108, number 1. 108, number 1. Here we go. 108, number 1. Alright, so we have that y, we're given that y equals a cosine of t plus b sine of t, using the result that y double prime equals negative y as a general solution of sine or cosine. And let's see if this works in Hooke's law, which says y double prime is negative y also. So y prime would be what? Well, let's see. The derivative of cosine is negative sine, so negative a sine of t, and the derivative of sine is a cosine, so plus b cosine of t. Now let's differentiate again. The derivative of sine is a cosine, so negative a cosine of t. The derivative of the cosine is negative sine, so negative b sine t. And isn't that exactly the opposite of y? Okay, perfect. Now let's say if we plug in the initial condition y of 0 is 5, then we get that y is 5 when t is 0. Now sine of 0 is 0, cosine of 0 is 1, so a is 5. Alright, so we get a is 5 from that. And the second initial condition is y prime is 0, y prime of 0 is 0. So y prime is 0 when t is 0. Whoops. Cosine is 0. Second line. Whoops. Whoops. And again, sine of 0 is 0, so the 8 drops out. Cosine of 0 is 1, so b equals 0. So we get that y of t is a cosine t, but a is 5, right? So 5 cosine of t. Clean that up a little bit. Plus b sine t, but b is 0, so there you go. So there's a particular solution. So if we're solving y double prime equals negative y with y of 0 is 5 and y prime of 0 is 0, and we use this as our general solution, this is our particular solution to that second order differential equation, which is not variable separable, unless y double prime means acceleration, and then you can call that dv dt, and we can play around with stuff like that. Solve for v, like we've done. But anyway, let's leave it at that. Alright, let's try another one like that. Number 2. Let's see, what's number 2? Number 2 says the force equation for a spring governed by Hooke's law is all the same stuff. But now let's say that k doesn't equal m, and we can write y double prime equals negative ky over m y as y double prime plus k over my equals 0. And just for general sake, let's call that constant k over m omega squared. You'll see why in a minute. Show that the general solution of a differential equation of the form y double prime equals omega squared y equals 0 is y equals a cosine omega t plus b sine omega t. So when we're solving second order differential equations, we're basically guessing the solution. We guessed that in number 1 that the solution had to do with a linear combination of sine and cosine. Now we're guessing that the general solution has to do with a linear combination of cosine omega t plus sine omega t. Alrighty. And find the constants omega a and b, given that omega squared equals k over m is 4, and the initial conditions that y of 0 is 1 and y prime of 0 is negative 6. Again, y of 0 is 1 inch, and y prime of 0 is negative 6 inches per second, so it's stretched out 1 inch, and it's moving in the negative direction. So it's in motion. Okay. So here we go. So now our general solution is, well, this is what we're solving. We're solving y double prime plus omega squared y equals 0, and with the initial conditions that y of 0 is 1 and y prime of 0 is negative 6. A little different, inches per second and 1 inch. Okay. So we're given that the general solution looks like this: a cosine omega t, omega is some constant, the frequency, right, of oscillation, plus b, a and b will affect the amplitude, sine of omega t. Alrighty. So what we want to show that y double prime plus omega squared y is 0, right? So we need y double prime. Here's y prime. So derivative of the cosine omega t is negative omega sine t, sine omega t, right? Because of the chain rule. So negative omega a sine omega t, because the derivative of sine of stuff is negative cosine of stuff times the derivative of stuff, which is omega. Omega is just constant. Plus, let's see, the derivative of sine omega t is cosine omega t times omega. So how about we write omega b cosine omega t? All right, good. And so y double prime, what is it? Well, let's differentiate sine omega t again, and we get another omega, and we get a cosine. So negative omega squared a cosine omega t. Okay, good. And when we differentiate cosine omega t, we get another omega times negative cosine omega t. So minus omega squared b, and the derivative of cosine is negative sine of stuff, and we did the chain rule. And isn't that negative omega squared times y? Because y is a cosine omega t plus b, sine omega t times negative omega squared will give you that, right? So we showed it, we proved it. Good, that works. So y double prime plus that would be 0. Perfect, that's it. All right, good. Now, given that omega squared is 4, let's solve. Alrighty, extend page. So now we're solving this. Y double prime plus 4y equals 0 with these initial conditions. I didn't apply the initial conditions yet. Okay, there you go. Alright, so y equals a cosine 2t, because if omega squared is 4, omega is 2, plus b sine 2t, so the frequency of oscillation is 2, the period is pi, the period is 2 pi over the frequency, and y prime, I only need y prime now because I got the initial conditions for y of 0 and y prime of 0, is, let's see, the derivative of the cosine of 2t is negative sine of 2t times 2. Alright, good. And the derivative of the sine of 2t is cosine of 2t times 2. Okay. So let's plug in some initial conditions. Let's see, y of 0 is 1. So when y is 1, t is 0. That's convenient that t is 0, so the 2 drops out, really. And again, the sine of 0 is 0, cosine of 0 is 1, so a is 1. Alrighty. And the y double prime of 0 is negative 6, so negative 6 equals negative 2a sine of 0. That drops out because sine of 0 is 0. plus 2b cosine of 0, because 2 times 0 is 0. Cosine of 0 is 0, 2b times, cosine of 0 is 1. 2b times 1 is 2b, so b is negative 3. Alright, so here is your particular solution. Again, this is your general solution. But the particular solution is y equals a, which was 1, cosine of 2t, plus b, which is negative 3, sine of 2t. So this is your particular solution. So we solved this differential equation with these initial conditions, a second order differential equation, based on our power series solutions and some assumptions. Okay. So let's see about this. Let's try number 4. Alright, so I'm going to skip over to number 4. Leave the rest as exercises for the reader. Alright, here's a pendulum. So a pendulum of length L feet makes an angle x radians with a vertical. When x is small, the motion of the pendulum can be modeled by this second order differential equation. Again, x is the angle. So x double prime equals negative g over Lx, which is a similar differential equation that we just solved. Then we just solved y double prime equals k, negative k over m times y. Yes, we did. So it's very similar. Where g is the acceleration due to gravity, and L is the length of the pendulum. All right, so solve this differential equation given the initial conditions. X of 0 is 0, y prime of 0 is v0. So at t equals 0, the angle with the vertical is 0, so the pendulum is actually vertical. But it's in motion. X prime of 0 is v0. If that's positive, I guess it's moving to the right. Interpret the solution. Then solve it for a different initial condition. X of 0 is x0, and y prime is 0, 0. So it's not moving, but the angle is some initial angle, x0. Interpret that result. And then how is your solution affected if x0 is increased? In other words, how does b, the solution to b, change? And how is the solution affected if L is increased? All right, well, we'll talk about that. All right, so here we go. So here's number 4. So we have x double prime plus g over Lx equals 0. X of 0 is 0. X prime of 0 is some initial velocity, v0. Okay? Again, we're going to start with our assumption that the general solution is x of t equals a cosine omega. Now, if g over L is omega squared, omega is rad g over L, some constant, times t, plus b sine, the same constant, rad g over L times t. Alrighty. And x prime of t is going to be, again, the derivative of the cosine of stuff is negative sine of stuff, rad g over L, times the derivative of the stuff. And we already had an a out here. That's g over L. And the derivative of the sine of stuff is cosine of stuff times the derivative of the stuff. So plus the derivative of the stuff times the b that was already there. That's a g. Alrighty. Now let's plug in some initial conditions. Let's see, extend the page a little bit. Alright. So if we plug in that, let's see here, x of 0 is 0 and x prime of 0 is, you know what? Let's not put that here. I'm going to put that down here. Alright, so there's my general solution. Right, x of t is my general solution. So what if x of 0 is 0 and x prime of 0 is v0? Alright, so let's see. In the first equation, x is 0 when t is 0. So we get 0 equals a cosine 0 plus b sine of 0. Again, sine of 0 is 0, so, and cosine of 0 is 1, so a is 0. And then v0 is x prime when t is 0. So you get negative rad g over LA sine of 0, again sine of 0 is 0, so it drops out. Let's just be sloppy. Plus, what is it, rad g over L times b times the cosine of 0. And again, the cosine of 0 is 1, so you get that b is rad L over g times v0. Alright, so what's your particular solution? X of t is a cosine rad g over LT, but a is 0, so it drops out, plus b sine rad g over LT, but b is this crazy constant. It's rad L over g v0 sine of rad g over L t. Alright, so let's talk about how that solution is affected. Let's see. So as L increases, so if L increases the length of the pendulum, what happens? Then two things happen. The amplitude increases, the amplitude of oscillation of the pendulum about the vertical, right? Because look at the L here, right? So as L gets bigger, the amplitude gets bigger. So amplitude increases, and as L gets bigger, the frequency decreases, because look at where the L is there. So frequency decreases. Okay. All right. How about the other initial condition? The other initial condition was x of 0 is some number of radians, but x prime at 0 is 0, so it's not moving. So it's at the end of its swing, let's say. A certain number of radians off the vertical x0, and it's not moving, then it's going to come back. Alrighty, so let's do the same thing. So in the first equation, we get that x0 equals a cosine of 0 plus b sine of 0. Now, the sine of 0 is 0, it drops out. Cosine of 0 is 1, so a times 1 is a equals x sub 0, so we know what a is. And in the second equation, the velocity is 0 equals negative g over L sine of 0, that drops out because sine of 0 is 0, plus rad g over L b cosine. Now cosine of 0 is 1, so rad g over L b equals 0 makes b 0. So b0 and a is x sub 0. So your general solution now is, what is it? It's x sub 0, a cosine of omega, which is rad g over L, t. The t is not in the rad. So now what happens? Well, if x0 increases, the amplitude increases, right? Because look where x0 is. There's no x0 in the first example, so we didn't answer that question. Then the amplitude increases. And if L increases, like last time we were asking that question, then the frequency also decreases of oscillation. Then the frequency decreases again, because of where L is now. There you go. All right, so that was number 4. All right, one more. How about number 6? Now this one takes this mechanical model and shows how it actually works in E&M. So let's try it. Number 6. Skip that for practice. Okay. Second order differential equation, Hooke's law without friction. Packet 109 will add a friction constant related to the velocity, I suppose. Anyway, the equation for the charge Q of T on a capacitor in a circuit with an inductance L satisfies the differential equation L Q double prime equals Q over C, plus Q over C equals 0 or equals negative Q over C, where Q, L, C, and T have the dimensions or units coulombs, henries, farads, and seconds, respectively. And by the way, I is the rate of change of Q, which is called the current in amperes, but that's Q prime. And L and C are given as constants. All right. So given that L is 36 and C is 9, find a particular solution Q of t when Q of 0 is 6 and I of 0 is Q prime of 0 is 0. All right. Let's start there. So let's see. This is going to be a similar solution to what we just did. Let's see. So they gave us L is 36. So we got 36 Q double prime, and they gave us C is 9. So plus Q over 9 is equal to 0. If you divide everything by 36, you get Q double prime plus Q over 36 and 9, which is 1 over 36, 1 over 9 is omega squared. So omega is going to be 1 over 6, 1 over 3, 1 over 18, right? So anyway, so if this is 9 times 36, yep, that's right. That's a perfect square because it's over 9 and over 36. So omega squared is 1 over 324, so omega is 1 over 18. Isn't that 18 squared? Yeah, it is. Okay, good. Now, so let's say Q of t has a general solution A cosine omega t, but omega is 1/18th, right? So t over 18 plus B sine of the same thing. And Q prime then is, because we need Q prime to use the initial conditions, they give us what Q of 0 is 0 and Q prime of 0 is 4. No, Q prime of 0, Q of 0 is 6 and Q prime of 0 is 0. That's what it is. Okay. Alrighty, so let's differentiate this. The derivative of the cosine of t over 18 is negative sine of t over 18 times 1/18th, but I have an a in there, so a over 18. Alright, the derivative of the sine of stuff is cosine of stuff times the derivative of the stuff, but there was a b times the 1 over 18. Alright, now let's plug in some initial conditions. Q of 0 is 6. Q of 0 is 6. Huh? Alright, so in the first equation, Q of 0 is 6. So 6 equals A cosine of 0 plus B sine of 0. Again, sine of 0 is 0, so B drops out. Cosine of 0 is 1, so A equals 6. And the second initial condition was that Q of 0 was 0, so plug in 0, so Q prime of 0 is 0, so plug in 0 for Q prime. Equals, let's see, negative A over 18 sine of 0. Again, that drops out. The sine of 0 is 0. Plus B over 18 cosine of 0. Cosine of 0 is 1, so B over 18 is 0. That makes B 0. And there you go. So my particular solution, again, if this is the general solution, right? And the initial conditions were Q of 0 is 6 and Q prime of 0 is 0. Then my particular solution is, let's see, what do we get? That A was 6. So Q of t is 6 cosine of t over 18. And that just tells you how the charge changes over time on that circuit. Let's see here. Let me think here. All right, let's do part B. That was 6A. All right, might as well label that. 6A. Put a little A in here. Okay, so 6B. 6B. Now, what's B say? Suppose that Q0 is 0. So the initial charge in coulombs is 0. Okay, fine. And I of 0, which is Q prime of 0, is 4, which is 4 amps. And the maximum charge is 2 rad 2. Okay, coulombs. Find the capacitance if the inductance is 10. Alright, so what does that mean? Well, that means that, we're given L is 10, and we don't know C. We're going to figure it out. So if we divide by 10, we get this, because you know this, the general solution to this. So what is it? It's Q of t is A cosine omega t, but omega squared is 1 over t c, so omega is 1 over rad t, 10c I should say, 10c, and there's times t, plus b sine of the same thing. The c is in the rad, the 10's in the rad. All right, so what's the derivative look like? Q prime gotta be, let's see, negative a sine of stuff, rad 10c is just a constant, times the derivative of stuff, okay, plus, let's see, b cosine stuff times the derivative of the stuff, 1 over rad 10c. All right, let's throw in some initial conditions. All right, so we got that Q of 0 is 0. So in the first line, Q is 0 when t is 0. Again, sine of 0 is 0, so b drops out. Cosine of 0 is 1, so a equals 0. Okay. And also we're given that Q prime of 0 is 4. So 4 equals, let's see, negative a over rad 10c sine of 0, again that drops out, plus b over rad 10c cosine of 0, cosine of 0 is 1, so b over rad 10c is 4, so b is 4 times rad 10c. Okay, so what's your particular solution? Again, if this is the general solution right here. So it's a particular solution. We got a is 0 and b is 4 rad 10. Okay, so let's write that. So now we get that Q of t, a is 0, so is b, which is 4 rad 10c, sine of t over rad 10c. So the frequency is 1 over rad 10c, and the amplitude is 4 rad 10c. And since the midline is 0, the maximum charge is 4 rad 10c, so we can figure out c. When we max this out, we get 2 rad 2 is 4 rad 10c. Alright, how about we divide by 4? We get rad 2 over 2 equals rad 10c. Let's square both sides. Get 1/2 equals 10c. So c is 1/20th. And what's that? Farads. The capacitance is 1/20th of a farad. Alright, and that's the end of 108. There we go. Alright, bye-bye YouTube. That was fun.